So basically what happens when a parachutist jumps from an airplane? For instance, we have an airplane up here. Okay, let's assume this is our airplane. Okay, these are the rings. Parachutist comes down. What happens, the very first thing that happens is that initially, when the parachutist jumps, initially means when the time is 0, the parachutist has jumped. He has not yet started moving down with any velocity. He's just about to jump. He's just left the plane. At that time, his velocity is 0. Okay. Initially, he jumped from rest. We are assuming that. And then, when the velocity is 0, will there be any air resistance initially? Air resistance, since it is also related to velocity, air resistance will also initially be 0. Air resistance initially is 0. Then as the person accelerates, and if the air resistance is 0, that means the force that he experiences in the upward direction, that's also 0, because air resistance is the force that acts in the upward direction. And in the downward direction, it's the weight. So if the upward force is 0, the net force is equal to the weight. And if the net force is equal to the weight, then the acceleration of this person initially is 9.81 meters per second squared. Acceleration of free fall. These are all the quantities that are present initially when time is 0, when the person has not yet started going down. When the velocity is 0, force is initial air resistance force due to air resistance is 0. So this is the direction of air resistance. And while he is falling due to his own weight. And we know that weight is equal to mg, and g is the acceleration of free fall. Acceleration of free fall initially is 9.81. Now, as due to this acceleration, what will happen to the velocity? It will start increasing from 0 to a larger value. The velocity will start rising. As the velocity starts rising, the air resistance also gradually increases. Okay, the air resistance, the resistive force also starts increasing. And if the air resistance or the resistive force starts increasing, that actually means the net force acting downwards. The net force downwards. The net force or the resultant force, which is actually the weight minus the air resistance. It is the weight minus the air resistance. So as the velocity increases, the resistive force starts increasing. And if the resistive force starts increasing, what will happen to the net force? It will start decreasing because it's being subtracted from the weight. And a time will come when this resistive force equals the weight. A time will come when both of them will balance each other out. And if they will balance each other out, what will happen to the velocity of F net? The velocity of F net would equal 0 at that particular moment, and whatever velocity this velocity has reached, that velocity would become constant at that particular point. Let it be 5 meters per second or greater value, or let's say 10 meters per second or any other value. But at any velocity's value, whenever the net force equals 0, the velocity will become constant because the air resistance, the acceleration has become 0. Due to this, the velocity will become constant at its maximum value, and as it becomes constant, it will fall down and hit the ground. It will terminate its journey with that particular velocity. So that's why that constant velocity is called the terminal velocity. Now, each and every event in the correct sequence should be on your fingertips from here, because this is no less than a 5-mark question. Okay. What happens to the velocity of a parachutist as he jumps down? So this is all of the stuff that happens to him. Initially, his velocity is 0, but his what is his acceleration? It's 9.81 meters per second squared. As time passes, velocity starts increasing due to the acceleration. If the velocity starts increasing due to the acceleration, then what happens to the air resistance? Air resistance also increases with the velocity. Increase in air resistance then adversely affects the resultant force, and increase in air resistance decreases the magnitude of the resultant force, due to which the magnitude of the net acceleration downwards, this acceleration also starts decreasing. And then as this acceleration reaches 0, the velocity becomes constant, and that particular velocity is called the terminal velocity. Is this clear? If I were to draw this motion on a graph, it would look somewhat like this, a graph of velocity against time. So initially the velocity was maximum, right? So sorry, initially velocity was 0, so this graph will start out from 0. Then initially the acceleration had a maximum value of 9.81. The acceleration is represented by the gradient of this graph, by the slope of this graph. So the slope initially is going to be maximum and will be constant. Let's assume it's constant. And as time passes, this slope, it starts decreasing. The graph slope will also start curving. And then a time will come when the slope, the graph would become horizontal. And at that particular time when the graph becomes horizontal, that's the constant terminal velocity. Horizontal graph or the curve or the flat curve means that the velocity has now become constant at that particular value. That constant velocity is the terminal velocity. Okay, so initially the acceleration was maximum, it was 9.81 initially. Then the acceleration starts falling, decreasing and decreasing and decreasing, and over here the acceleration becomes 0. And what happens to the velocity? The velocity, regardless of the decrease in acceleration, still rises. If you look at the y-axis value, the velocity starts increasing. Initially, it was increasing at a high rate, but then it increases at a decreasing rate. It increases at a decreasing rate. Okay, increasing at a decreasing rate actually means increasing at a slower acceleration or at a lesser acceleration due to the curve present in this graph. And then when the curve flattens out, when the curve becomes horizontal, that's the point where the acceleration has become 0. Now, all right, question 17. A guitar produces sound by making a series of strings vibrate. To produce the correct frequency of sound, the tension in each string must first be adjusted by turning a tuning peg attached to a rotating cylinder. Okay, this is your rotating cylinder and this is a string. Okay, and this is your tuning peg. You rotate that tuning peg, you rotate the cylinder, and then that tightens the string, produces some tension in the string. A new string is attached to the guitar and wound around the rotating cylinder until the string just begins to tighten. The original length of the string was 0.6 meter. The rotating cylinder is turned by adjusting the tuning peg until the tension in the string is 190 Newton. Show that the string will extend by 8 millimeter. A diameter of the string is given to you. Young's modulus of the string is given to you. All right, so this is a pretty basic question of Young modulus. They've given you the Young modulus. They've given you the diameter. All they need you to do is just show that the extension is 8 millimeter. Like they've even given you the answer. They want you to show this that the extension is this much, and the original length is given to you, and the tension, meaning the force in the string, is also given to you. So do you remember the formula for Young's modulus? Right, so this is your formula, FL over AE. All you need to do is just find out the value for E. Okay, so let's make this small e the subject. So F is given to you is 190, L is 0.6. Cross-sectional area, they haven't given you the area, but rather they have given you diameter. Where is it? Here it is. Diameter is given to you. Can we calculate the area? Definitely we can calculate the area. Area is pi d squared upon 4. So pi multiplied by the diameter, which is 3.3 raised to the power of -4.
Why did you choose to use pi d squared over 4?
Because the diameter is given. Diameter is given. You can use both the formulas. They'll give you the same answer. Okay. They'll give you the same answer. Okay, can you please calculate the answer? Pi d squared upon 4.
(2.59 into 10 to the power -4).
Wait, this answer.
Yeah. Oh wait.
I'm getting 8.55 raised to the power.
I did not square it.
Oh no, that's
8.55 into 10 to the power -8.
Okay, yeah, that's the answer. So FL over A, which is 8.55 raised to the power of -8, multiplied by the extension, which is sorry, not the extension, multiplied by the Young's modulus. Young's modulus is 170 and it's giga. Giga means 10 raised to the power of 9. Okay, gigapascals. So now all you need to do is just simplify this thing. It's going to be 190 times 0.6 divided by the answer multiplied by 170 times 10 raised to the power of 9. This turns out to be 7.84 raised to the power of minus 3. 7.8 raised to the power of minus 3. If I were to round it off, it's going to be 8 raised to the power of minus 3 meters. Minus 3 means millimeters, so it's 8 millimeters. Sure. Clear?
Yep.
Rotating cylinder has a diameter of this much. Calculate the number of turns of the rotating cylinder that are required to produce this extension. Okay, they've given us the diameter of the rotating cylinder over here, which is 9.2 raised to the power of minus 3. And they're asking us that to calculate the number of turns which are required, basically to produce this extension. So what is the total extension? Extension is 8 millimeters. So how many times do we need to wrap this 8 millimeter around this circumference? So first of all, you'll need to calculate the circumference of this circle, of this cylinder. The circumference has the formula of 2 pi r, which is equal to pi d, right? Pi multiplied by the diameter, which is 9.2 raised to the power of minus 3. This shall give you the answer of pi raised to the power of 9.2 times 10 raised to the power of minus 3, 0.0289 meters. Okay, now this is the circumference that you have. This is your extension. To calculate the number of turns, okay, this circumference means that for one turn, the length must be this much, right? And turning it around this cylinder once would require this much length of the wire. So how many turns are required if this is the total length? 8 raised to the power of minus 3. You cross multiply it, you get your answer. The value for x is 8 raised to the power of minus 3 divided by 0.0289, and this turns out to be 0.277. Weird answer. 28. This answer is correct. This is the number of turns. Well, usually they don't give turns in decimals, but anyways, this question had it in decimals. That this one says, it is important that the guitar strings have high elastic limit. State what is meant by the term elastic limit. Okay, what is elastic limit? I gave you the definition of elastic limit. Basically, the definition is the following. The max point till which or the max point after which the wire or the length of the wire does not return to its original value if the deforming forces are removed. Okay, so for the definitions, let's look at the marking scheme as well. Maximum stress force of which material will return it to the original length when the applied force is removed. Yeah, that's the same thing. The maximum point after which the point it will return back to its original value. Okay, then after this part, explain why the guitar string should have high elastic limit. Okay, so for the elastic limit, these guitar strings, okay, elastic limit is important in order to allow them to return back to their original value after the last deforming forces are removed. First of all, it prevents it from breaking. Well, high elastic limit means high breaking point as well. And secondly, the strings can return back to their original point, so this maintains tension in the string, in the wire as well. Thirdly, the strings might be able to withstand this force and then return back to their original point. So it's the same thing. If given us 3 marks, so we'll need to think of at least 3 points. Let me read this out. Okay, so high elastic limit means more force can be applied without permanently deforming it, without permanently extending the wire when it is plucked. Then we could say, yeah, if the plucking is there, after it is plucked, apart from that, if the fire does not permanently extend, then that means it will stay in tune. The guitar will stay in tune, right? The guitar does not go out of tune. So I guess that should be enough. 3 marks. High elastic limit means more force can be applied without permanently extending it, without permanently deforming it, so the guitar stays in its tune. And yeah, that's it. 3 marks. Up over a crossbar as shown in the diagram over here. The athlete runs down the runway at high speed and places the end of the pole in the vault over here, vault box. The pole bends and straightens, then moving the athletes upwards. Then at the maximum height, the athlete lets go of the pole. Okay, the athlete comes over here, he goes up, then at the maximum height, lets go of the pole, and then he hits down. Explain how using the pole enables the athlete to reach a greater height than by jumping. Your answer should be in terms of energy transfers involved. Okay, first of all, it's elastic. The pole was elastic. Long flexible pole is there. Flexible, anything that's flexible, it has the ability to store elastic potential energy. Store elastic potential energy. Then that means the kinetic energy with which the person runs, it gets converted into some of the elastic potential energy. Then as the person jumps, his kinetic energy is also there. If the kinetic energy, it gets converted into only gravitational potential energy, then there's a high chance that the person would fall quickly. But if that kinetic energy also converts into elastic potential energy, that elastic potential energy would then later allow this that elastic potential energy would then convert into kinetic energy, and then that kinetic energy, that extra kinetic energy, would allow this person to go up. Okay, so we have to give it in terms of energies, and the elastic potential energy reference is very, very important. Okay, it's for 3 marks. Again, at least 3 points should be there in your answer. So kinetic energy of the person gets transferred into elastic potential energy, is transferred as the athlete jumps and bends the pole. Then when the pole starts straightening, when the first of all, as he bends the pole, he converts his kinetic energy into the elastic potential energy. He comes running, he has some kinetic energy. Then as he bends it, the kinetic energy gets converted into elastic potential energy. And then as this pole, it straightens, its elastic potential energy is transferred into the kinetic energy and the gravitational potential energy of the athlete again. Okay, so as the pole straightens, the elastic potential energy is converted to kinetic energy plus gravitational potential energy. Why kinetic energy again? Because as the athlete will be going up, he will be going up with some velocity, right? Velocity means presence of kinetic energy. And as this athlete would be gaining height, then that would mean it would have some gravitational potential energy at the same time. So potential energy gets converted into kinetic energy. Greater. Then after this,
Hello?
yes, hello. As this person without the pole jumps, as this person jumps without the pole, if there is no pole, you have to compare it with without the pole as well, right? So if this person jumps without the pole, then that means his entire kinetic energy would only be converted into gravitational potential energy. But at that time, why doesn't he jump higher? Because not all of the kinetic energy gets converted into gravitational potential energy. Some of the kinetic energy might be lost in the form of heat or in other forms, for example, sound or heat or any other substances, the frictional forces, etc. But as this person uses a pole, the efficiency of transfer of kinetic energy to the gravitational potential energy, it increases. So without a pole, the transfer from kinetic to potential energy, the transfer process would be less efficient. Okay, so I think this covers up the 3 points. As the pole bends, kinetic energy is transferred to elastic potential energy. As it straightens, it is transferred back to gravitational potential energy and kinetic energy. And then greater heights can be reached when the energy stored is in the pole is greater than in the legs when jumping. More of the initial kinetic energy transferred to GPE in pole vaulting. The pole is more efficient at converting kinetic energy into gravitational potential energy than legs alone. So this was our third point. Potential only needs to be included once for GPE and once for EPE, allow CAIE and stuff like that. Okay, so yeah, we got the 3 points. Okay, this is the third point, that the pole is more efficient at converting the kinetic energy into vertical gravitational potential energy than the legs alone. So that's why it reaches at a higher point. Okay, so did you notice one thing? That this third point was actually what was the main point. But the first 2 points, they actually describe the conversions in energy. They actually just answered this part of the question. So the 3 marks are not entirely for the question itself, but rather the 2 marks are for making a background for the question. So you should always think about some background knowledge before answering the main fact, okay? In order to get all the marks. That's the trick in solving physics papers. And I've noticed one thing, that in the latest papers, the marking scheme has become even more specific, like just 1 point, 1 mark, fewer points for each marks. See, just 2 points, not like the previous marking scheme, which had multiple points for each mark. So you have to have a lot of marking scheme practice. Please try learning and reading the marking scheme points as well, because in physics, the key points, these wordings are very, very important, okay?
Okay, can you share your answer again? Okay.
Yes. As the athlete reaches a maximum speed of 9.4 meters per second before placing the pole in the vault box, you may neglect the frictional forces and any work done by the athlete's muscle after the pole enters the vault box. The athlete has a horizontal velocity of 1.1 meters per second at a maximum height. Calculate the maximum possible change in height of the athlete's center of gravity. Okay, So basically, center of gravity means actually the athlete itself. They are asking us that the maximum speed of the athlete was 9.4 meters per second. That actually means that as the athlete moved up from here, the speed was 9.4 meters per second. And then as he reached the maximum point, his velocity was 1.1 meter per second, and that's the horizontal velocity. And they're asking us calculate the maximum possible height that can be obtained by the center of gravity of this athlete. Center of gravity is that particular point from where the weight of the person appears to act. So they're just asking us to calculate the maximum gain in height. And they're asking us to neglect any work which is done by the muscles. So neglecting the work actually means the change in kinetic energy of the athlete is equal to the change in gravitational potential energy of the athlete. Okay, this is the first point that should come in your mind. What is the change in kinetic energy of the athlete as he moves from this velocity to this velocity? We can calculate that using the formula half m v1 squared minus v2 squared, right? The initial and final velocities. This is not the same as v1 minus v2 the whole thing squared. Okay, this is not the same as that. This will give you a different answer. So now you don't know the mass of the athletes, doesn't matter because the gravitational potential energy also contains mass in its expression. You'll get cancelled out anyway. Okay, now all you need to do is just find out the value of h. So half multiplied by the velocity is 9.4 squared minus 1.1 squared, which is equal to g, which is 9.81 multiplied by the height of the athlete that he needs to gain. And now calculate the value for the height, which is how much?
Points.
And divided by 9.81.
4.
What is the answer? 4.4?
4.
4, okay, meter. This should be the maximum change in height or maximum gain in height actually, they should rather say. That's the answer. Yep, that's the answer. Then next part says, consider the pole to behave as a spring of stiffness this much. Stiffness,
They
what is
used
stiffness?
two significant figures.
Yeah, but 3 significant figure is also fine. You can either give your answer to 2 or 3 significant figures. Well, if the latest marking schemes are giving you answers to 2 significant figures, leave it in that form. But 3 is also acceptable, okay, remember. Well, the 2 is given to you because the data is given to you in 2 significant figures.
Right.
That's why, okay. But 3 is also fine. Now coming back to this question, it says the stiffness is given to you 850 Newton per meter. This is also in 2 significant figures, look at it. The distance between the two ends of the pole decreases by a maximum of 2.1 meters during the jump. This is the extension or the compression. Calculate the maximum proportion of the initial kinetic energy stored in this pole. Mass of the athlete is given to you 78 kg. All they want us to do is just assume that there is a spring instead of a pole with a stiffness of this much. Stiffness is another name for the spring constant K. Okay, the spring constant K given to you is 850 newtons per meter. The mass of the person is given to you as 78 kg. The maximum extension or the maximum compression, meaning the value of x, is given to you, which is 2.1 meters. We need to calculate the maximum proportion of the initial kinetic energy which was stored in this pole to change the height by this much. Okay, so all we need to do is just find out the elastic potential energy that was stored inside this spring due to the change in this thing. What's the formula for elastic potential energy? Well, why am I saying that? Because the change in elastic potential energy is the change in kinetic energy, right? Kinetic energy got converted into the change in elastic potential energy. Again, I need to write this statement as well. This statement usually carries the mark as well. Okay, so do not forget to write the statement. Change in kinetic energy equals change in potential energy. Now, kinetic energy, we need to calculate the change in kinetic energy. So that we'll need to
Half k
calculate.
x squared.
Yeah, half k x squared.
X squared.
Yeah, so half multiplied by k is 850. The value for x is 2.1 squared. This turns out to be half times 850 times 2.1 squared, which is 1874.25. Yeah, 1874.25 joules is actually the gain in the elastic potential energy. They want us to calculate the maximum proportion. Proportion means ratio, right? Ratio. Proportion means ratio. They want us to calculate the ratio of this energy to the total initial kinetic energy. What was the initial kinetic energy with which the athlete jumped? Initial KE can be calculated using what formula? Half mv squared? Half times, what is the mass? Mass given to you 78 kg. What is the initial velocity with which the athlete jumps? It's 9.4 meters per second, right? This is the initial velocity with which he starts jumping, starts his motion. So this is going to be 9.4 squared. And the answer that turns out to be is half times 78 times 9.4 squared, 3446.04. Now we need to calculate the proportion. Proportion means ratio. Proportion of this that got converted into that. So this energy divided by kinetic energy. It's going to be 1874.25 divided by the 3446.04, and this turns out to be 1874.25 on this answer. 0.54 is the proportion or the ratio. Clear? That should be strong enough to withstand the whole of the load of this athlete, right? So the material should be strong enough to withstand the whole the load of the person, and apart from that it should be elastic as well. And if it is elastic, then its elastic limit should also be high, so that it doesn't get deformed permanently. Okay, so these are the two properties, I guess. Okay, what is the breaking point called and what is the elastic limit called? So basically the breaking point of the spring, the breaking point, the point till where it breaks, it can also be related to a property.
And the point until which it can bear like the maximum stress.
Yeah, what is that point called? What is the stress called? The maximum stress that
The tensile strength.
ultimate tensile stress. Okay, so the pole should have high ultimate tensile stress. Ultimate tensile stress. Okay, so this is one point that we stated. Now what's the explanation of this point? So that it doesn't break easily. So that it does not break and is able to bear the weight of the athlete. Okay, and what's the second point? The second point, which I told you, is elastic limit should be high. Elastic limit should also be high. So that the pole
Can return to its original shape.
Yes, definitely. Could regain its original shape or return to its original shape or could straighten up. Okay. Again, theoretical question, so let's refer to the marking scheme as well. Strong ultimate tensile stress, high elastic limit. Oh, so it does not bend permanently, so it does not break easily. Wow, we got both the points and both the marks. Congrats. Are we done? Oh, we are done. Oh, let's go through this list of formulas as well. Acceleration of free fall is
What year was this?
2018, October, November.
So the new specification.
Okay, so which of the following is an equivalent unit to ampere? Ampere is a unit for current, right? I, current by definition is rate of flow of charge, matlab charge per unit time. Unit of charge is coulomb. Unit of time is second. So what does it become? Coulombs per second. Coulombs per second, option C. Clear? Okay. Number 2. Distance between an approaching aircraft and an airport can be determined using pulse echo technique with radio waves. अच्छा pulse echo technique कुछ नहीं है, यही है कि ये जो आपके पास एक एयरक्राफ्ट है और यहाँ assume करते हैं टावर है, ठीक है, यहाँ से पल्स भेजेगा, वो पल्स जाएगी रेडियो टावर से टकरा के वापस जब इसको आएगी, ठीक है, तो ये बीच का जो डिस्टेंस है ना, ये s होगा, तो कितना डिस्टेंस रेडियो वेव ने ट्रैवल कर लिया होगा, जाने का और आने का टोटल डिस्टेंस ट्रैवल्ड इज 2s. रेडियो वेव की स्पीड इज द सेम एज द स्पीड ऑफ लाइट 3 raised to the power of 8. इन दोनों को यूज करते हुए वो टाइम निकाल लेगा, सॉरी टाइम भी इनके पास कैलकुलेट हो जाएगा कि कितने टाइम में वो वेव वापस आई है, तो टाइम और स्पीड को यूज करते हुए डिस्टेंस निकाल सकते हैं, ठीक है। अब ये कह रहे हैं कि द टाइम बिटवीन द पल्स ऑफ द रेडियो वेव्स बिटवीन द एमिटेड एंड द रिफ्लेक्टेड पल्स बीइंग रिसीव्ड इज t, ठीक है, टाइम दे दिया है इन्होंने। The velocity of radio wave is c, speed of light. Which of the following expressions can be used to determine the distance of the aircraft from the airport? अब distance की वैल्यू निकालनी है। अच्छा, distance from the aircraft to the airport तो ऐसे, लेकिन रेडियो वेव में कितना ट्रैवल किया है? डबल ऑफ दैट, राइट, जाने का और आने का। तो distance is equals to speed upon time. Time is equals, sorry, distance is equals to speed multiplied by time, क्योंकि speed की वैल्यू क्या होती है भाई? Speed is equals to distance upon time होता है ना। रीअरेंज करेंगे तो speed multiplied by time is distance. So speed की वैल्यू c है, टाइम की वैल्यू t है। अब s को अगर आप सब्जेक्ट बनाएंगे तो ये क्या बन जाएगा? ct upon 2, c into t upon 2. That's the answer. Part B. Clear?
Yep.
Okay. A person hears a sound from a siren of an approaching police car. Which of the following properties of the sound waves does not change if the car stops moving? Okay, if the car stops moving, which of them does not change? Frequency. If the car stops moving, will it change? Doppler's effect याद है? Person hear कर रहा है. Doppler's effect में पुलिस कार अप्रोच कर रही है तो उसे कुछ और फ्रीक्वेंसी सुनाई देगी, और जैसे ही वो स्टॉप करती है उसे एक्चुअल फ्रीक्वेंसी सुनाई दे देगी. So has the frequency changed? Right? Frequency changes because of the Doppler effect. Frequency change होगी नहीं. Time period. Will the time period change?
Wait, this is Doppler effect?
Yeah, due to Doppler effect it will change, right?
No, I don't. Doppler effect is not a part of our syllabus.
Okay, so the diagram shows 3 energy levels in an atom. Which of the following electron transitions between energy levels would result in emission of electromagnetic radiations of highest frequency? Okay, let me tell you something. Energy is related to the frequency directly, okay? And if you remove out this proportionality sign, you'll need to plug in a constant and an equal to. This constant is the Planck's constant. Okay, you need to learn this equation. Now, if the energy is proportional to the frequency, this means that the greatest difference in the energies, the highest frequency will be emitted. Now remember one thing, when electrons move from higher, this is higher energy level, this is lower energy level, okay? If the electrons move from high to low energy level, then the difference in between these two energy levels will be emitted out, okay? Remember that. And if the electron wants to move to a higher energy level from the lower one, then it will have to absorb an energy equivalent to the energy that was lost over there for promotion to a higher energy level. So now they're asking us which of these transitions would result in the greatest frequency of energy transmission. So that would be the greatest distance, right? From 3 all the way to 1. If the electron is transited, then it would emit out the photons of the highest energy. Photon means, photons are actually packets of energies, okay, particles of energies. So it would emit out energy of the highest frequency. So 3 to 1 is the answer. Understand? Now, the diagram shows parts of the rays of light into a glass block. This is your glass block over here. This is air. Okay, now the critical angle of the glass air boundary is 40 degrees. Acha, glass air boundaries critical angles. For this, you'll first need to understand what reflection is, what incident and refraction is. So if, for example, this is our glass surface, normal to the surface, we draw an imaginary line which is called normal to the surface. Okay, it is at a 90 degrees. This line is called normal. If a light ray comes and is incident on this surface, the angle that this light ray makes with the normal is called the angle of incidence. And this is air and this is glass. Okay, glass is a denser medium as compared to air. So whenever a light ray moves out from a lighter medium to a denser medium, it changes its path, and it bends towards the normal. Okay, the light ray bends towards the normal. This angle that that this bended wave has made with the normal is called the R. By R I mean the refracted angle or angle of refraction. Refraction means bending of light when it enters from a lighter to a denser medium. Now, what do they mean by critical angle? Critical angle is basically also an angle of incidence for which the refracted angle equals 90 degrees. Clear? You understand what critical angle is?
Yep.
It is a angle of incidence for which the refracted angle is 90 degrees. And in case of critical angle, we do not incident the ray from a lighter to a denser medium, but rather the ray is incident from a denser to a lighter medium, meaning in the other way around. For critical angles, if this is glass and that's air, the ray will enter from outside, okay, from here. So this is our incident angle, which is our critical angle. And if this is our critical angle and this is our incident ray, then the refracted ray must be such that it must be making an angle of 90 degrees with the normal. Okay, so this angle, what is this angle called? This is called the critical angle. Now in this case, they are saying that the critical angle for the glass air boundary is 40 degrees. 40 degrees means that this angle, if is placed at 40 degrees, then the refracted angle would be 90. Which dotted line would represent the continuing pathway of the ray light? If you look at this diagram, the ray is coming from air, enters the glass. So during this, the ray will bend away from the normal, right? This was the incident angle, this was the refracted angle. Actually, it bent towards the normal. The refracted angle is less than the incident angle. But now within the glass bead, as this ray continues and reaches here, this is an example of moving from a denser medium to a lighter air medium, right? It's this situation over here, from glass to air, from glass to air. Now they told us that the critical angle is 40. If this ray would have incident at this point at an angle of 40 degrees, then we would have gotten this pathway of 90 degrees. But now, since it's not incident on this glass bead at 40 degrees, but rather it is incident at an angle lesser than 40 degrees. It's incident at an angle of 30 degrees. But is this 30 degrees the same as the angle of incidence? Is this 30 degrees the angle of incidence or not? Yes or no? Is it angle of incidence or is it not the angle of incidence?
No, it's not.
Why not?
Because you have to subtract it by 90.
Subtract it from 90 and you'll get your incident angle. Reason, because the incident angle is always made
Between the normal,
the normal and the ray.
The normal angle.
it is always made between the normal and the ray. And if you calculate the incident angle, it's 60 degrees in this case. 90 minus 30 is 60. This 60 degrees is actually greater than the critical angle. If your incident angle is greater than the critical angle, then a phenomena called total internal reflection occurs. You remember total internal reflection? Meaning,
Yes.
this ray, when it hits here, it will get reflected back. And this A is the answer. A displacement time graph for the particular point on a transverse wave is shown 2 times as marked X and Y. Okay, this is X and this is Y. These are two different instants. Which of the following represents a change in displacement of this point between times X and Y? Okay, the point which is in between X and Y, will it go up or will it come down? Okay, if you look at these points, all of these points are coming down. These points have to come down, all of these. And actually, no, not all of these. The points which are above the line will come down. The points which are below the line will go up. So these points are again above the line, it'll have to come down. This should be option number D. Clear?
Yep.
Again, below the line, they'll go up, then above the line, come down. Fluorescent lamp has a power input of this much. The rate of transfer of thermal energy by the lamp is 9.8 volts. The remainder of energy becomes light. Which of the following is the efficiency of the lamp? Efficiency is actually the useful power output upon total input. The total input is 14 watts. The useful power output, is it 9.8? Is the thermal energy the useful energy in case of fluorescent lamp? Or is it
Thermal energy.
Or is it the bright light that's the useful energy?
So the useful energy is the bright light.
Yes. So will we need to subtract them to calculate the power that
Yep.
converted into the bright light? It's going to be 14 minus 9.8, and this turns out to be how much? 0.3. Option A. And let's move on. Question 8. Which of the following quantities can be defined as energy transferred per unit charge, meaning energy upon charge? Any formula you remember?
The V.
V, correct. V, potential difference. Voltage, potential difference, right?
Yep.
The negative temperature coefficient of thermistor is connected in series with resistor. They are connected as shown. Okay, don't get confused by this term, negative temperature coefficient. Negative temperature coefficient actually means that as temperature rises, its resistance falls. This is what it actually means, okay? And this is what you already know for thermistor, right? As the temperature rises, the resistance does fall, right? Now, which of the following graphs best shows the variation of the current with the temperature of the thermistor for a circuit as shown? Okay, this is your circuit. If the temperature will rise, will this resistance fall?
Yep.
If the total resistance decreases, that means the total current will increase in the circuit.
Oh, yes.
Okay, so now we should have a graph. Okay, initially, where is it? Yeah, when temperature is zero, the current should be almost zero. Well, actually not actually zero, but rather the current should have some value, because when temperature is going to be zero, the current will have a small value, not exactly zero, but small. Okay, A cannot be the answer because of course current will change. B, can B be the answer? Well, that when the temperature will rise, the resistance will fall, the current has to rise. B cannot be the answer either. Over here, the current is falling. Now it's either option C or option D. Okay, option C, as the temperature rises, the current will also rise. But will the current rise at an infinite rate after a certain point, or will the current become constant? If the temperature resistance of this thermistor will fall, but it will also have a certain lower limit, right? it won't fall all the way to 0. It will have a lower limit. Usually the values which are given for a thermistor are 10 to 100 ohms. So if the temperature, even if the temperature is very high, its resistance cannot go below 10 ohms. This means the resistance will still be there. And even if the resistance does decrease to 0, let's assume it does decrease to 0, the resistance of this resistor is still there, right?
So D.
So yeah, option D. It will become constant. Sound waves travel through air and pass into a concrete wall. The energy of the sound waves transmitted into the concrete wall is much less than the energy of the sound wave in air. Which of the following wave properties is the reason for this? Okay, so you have a concrete wall over here, and now the wave comes, hits it, but the energy with which it hits is not entirely transferred over here, but a very small proportion of this energy gets transferred. A large proportion gets, what does it get? It gets reflected. Option C. It will get reflected. 11. Okay, describe how a standing wave is formed. A very, very frequent question in both Cambridge syllabus and Edexcel. Okay, so stationary wave is formed when two waves traveling in the opposite direction, having the same speed, frequency and wavelength, and type, frequency, wavelength, type, and are coherent. Superimpose over one another, or overlap over one another, or meet one another. Superimpose. They result in nodes and antinodes formation. Nodes and antinodes formation. Due to destructive and constructive interference. Forming a standing wave. There, let's look at the marking scheme as well for it. Wave traveling in the opposite direction, superimpose, produce nodes and antinodes. See, we got our answers. We got all 3 points. But this descriptive form answer is quite reasonable. But all the 3 points that they wanted was different opposite directions, superposition, and nodes and antinodes production. That's it. Any answer having these 3 points will get full marks. Clear?
Yeah.
Okay, now an organ pipe is open at both the ends. Okay, we have an open pipe. There is an antinode at each end of the pipe. Of course, we know that from theory. Just determine the shortest length of the pipe required to produce a sound with a wavelength of 2.6 meters. Okay, so we need the shortest length of the pipe. Okay, this is our pipe. And we need its shortest length. Shortest length actually means the very first stationary wave. The very first stationary wave would actually have just 2 antinodes on both the ends. Okay, this is the stationary wave that will, this is the shape of the stationary wave that we will see. Okay, so somewhat like this. Okay, antinode at this end, antinode at this end, and node in the center. Now, what's the distance in between these two? This is your antinode. This is your antinode as well. I told you the distance between node to antinode is lambda by 4. Distance between node and antinode is lambda by 4. So both of them collectively would be lambda by 2. Clear? Entire distance, this one, is lambda by 2 between 2 consecutive antinodes. Think of it this way. This is your wave, complete wave. You're just dealing with this section from here to here. So you've removed out the two ends. Okay, is this clear? So lambda by 2 is the length of this wire, length of this pipe. So lambda by 2 must equal the length of the pipe. Okay, so lambda is 2.6. When you divide that by 2, it will give you 1.3 meters. Clear? Should I move on? A torch battery has an EMF of 1.5 volts. When connected to a torch bulb, the terminal potential difference is 1.2 volts. The current in the circuit is 280 milliampere. Calculate the internal resistance of the torch battery. Okay, so if you think about the circuit, it's going to look something like this. This is your battery having some internal resistance. Remember, I told you internal resistance is just a small resistor in series with the battery. This internal resistance is connected to some torch bulb. Let's assume this is our torch bulb with X. And this is the circuit. And this is entire battery. Terminal potential difference means the potential difference in between these two particular points over here, between the terminals of the battery. Okay, terminal potential difference is 1.2 volts. The current in this circuit is 280 milliamperes. And then they're asking us to calculate. Okay, let's assume the resistance of this this bulb is capital R, and internal resistance needs to be calculated. Now, the terminal potential difference. How can the terminal potential difference be calculated? Very simple. Terminal potential difference is always the difference of the EMF and the difference of EMF and potential difference and internal resistance will give you the terminal potential difference. Or let me talk about it this way. Okay, the current is 280 milliampere, and the total EMF of the battery is 1.5 volts. Let me erase out this voltmeter from here. Now, the EMF of the battery is just 1.5 volts, but what is reaching out of the battery? What is coming out of the battery? Meaning what is reaching this bulb is just 1.2 volts, right? It's not entire 1.5 volts. So this means how much is being dropped across the internal resistance, the difference of them. So voltage, volts dropped through the small r is 1.5 minus 1.2, which is 0.3 volts. Okay, 0.3 volts are dropped across the internal resistance. Can we use the formula V is equals to IR to calculate the internal resistance? We know the voltage of the internal resistance. We know the current that is flowing through it is 280 millivolts. The voltage of the internal resistance is 0.3. The current is 280 milli. Milli means 10 raised to the power minus 3 multiplied by R. And the value of R turns out to be 0.3 divided by 280 times 10 raised to the power of minus 3. And so the R turns out to be 1.07 or 1.1 ohms. Power transferred by the torch bulb. Power transferred by the torch bulb by this thing. Calculate the power transferred by this torch bulb means the power that it produces. The formula for power is voltage into current when both of them are given, right? The voltage across this power bulb is the terminal potential difference itself. It's 1.2. The current across the circuit or the current across this power bulb is also 280 milliampere. That's the answer. Turns out to be 0.336 watts or just 0.34 watts to two significant figures. Clear? Is this part clear? Okay, so think of it this way. You've got a bulb in the circuit. This bulb is connected to some power source or battery. Battery has an internal resistance, small r, and then this circuit is completed. EMF of the battery is 1.5 volts. The terminal potential difference, meaning the potential difference from here to here, difference in between these two potentials, which is registered by the voltmeter, is how much? 1.2 volts. So this actually means that the total voltage or the EMF of the battery is 1.5 volts, but how much is dropped across the internal resistance? It's going to be the difference of these two values, right? Right?
Yeah.
So if it's going to be the difference of these two values, this means that 0.3 volts has been dropped across the internal resistance, right? Because 1.2 volts is the only voltage that is reaching this bulb. Now, if 1.2 volts is reaching this bulb and the current through this circuit is 280 milliamperes, that means the current through this internal resistance is also 280 milliamperes, right? Because this is a series circuit. If this is the current and this is the voltage, can we use these two and use Ohm's law to calculate the internal resistance?
Oh, yeah.
The internal resistance, the voltage is 0.3 volts, current is 280 milliamperes times resistance, and resistance turns out to be 1.1. Clear?
Yep.
Now they're asking us to calculate the power in the second part, the power by this bulb. What is the current that is reaching this bulb? It's 280 milliamperes again. The voltage is 1.2 volts. The formula for power when both voltage and current are given to you is voltage multiplied by current. The voltage across that bulb is 1.2 volts. In this case, it's just the terminal potential difference that is reaching this bulb, right? Is that clear?
Yeah.
Okay, so this is 1.2. When it gets multiplied by the current that is passing through it, you'll get the power across this bulb. Okay, 0.336 or 0.34. Clear?